Our email ID, the official email ID info@vardeez.com. This is our WhatsApp number. You can ping us for any guidance if you need. And this is our website. That's www.vardeez.com. For any FRM packages, you can visit our website. Alright, so here's the syllabus for the FRM part 1. All the 13 chapters is included in this revision ebook that we've created, and this is something that all the chapters you will see the videos for. So let's just begin with the very first reading. So today we're going to be talking about the first chapter, okay, the fundamentals of probability, and we're going to be revising this thing. So let's just see what this chapter has to offer to us. Okay, so first off, the definitions. What is probability? So probability, it measures the chance or likelihood of any event happening. Okay, so in this entire chapter, and rather in, I would say, the entire statistics, it's all about the probabilities that we want to observe. Okay, the likelihood of something or any event that could happen. So that is the first definition of probabilities. Is there any properties to it? Yes, two properties. First one, second, the sum of probability of all the outcomes will be equal to 1. So if you have multiple events, A, B, C, D, whatever events that you have, when you sum it up, when you add it, okay, it's going to equal 1. It cannot go above 1 at any cost. So that's the very first probability. Second one, the probability of outcomes will be between 0 and 1, including both. Okay, so you can have the probabilities between 0 and 1. It cannot go beyond or above 1. It cannot fall below 0. That is in the negative terms. You cannot say probability of negative 0.5. There's nothing like that. It's within this range only the probabilities will fluctuate, always and always. What about random variables? So entire thing is all about random variables. 3 to 4 chapters is we're going to be spending on random variable. So it's a variable whose value is unknown to us. You can take an example of the stock price. We don't know what's gonna their value maybe tomorrow. All right, so something we do not know of, maybe stock prices. Volatility is another variable that we do not know. The options prices, the calls, the puts. Okay, the option, that's also the variables. It has a lot of variables like the volatility, the risk-free rate, so on and so forth. So all these things are random variables. What about event? Event is something, possible outcome of a random variable. For example, if you toss a coin, that's an event. If you do some experiment, that's an event. Event space, that means all the possible outcomes. Okay, so even negative outcomes, let's say that, for example, when you toss a coin, getting neither heads or tails is also part of the event space. Okay, so this was the first learning objective about the event and the event space. Okay, moving on to the types of probabilities that we have, and there are many different types. Okay, so just we go through these quickly. Okay, what is a joint probability? As the name suggests, joint means joining two events. So how do you find the probabilities for that? So when we say that event A and B, they both occur together, that's when we say that, okay, that's a joint probability. Notation wise, this is how it looks like: probability of A and probability of B. So I can say that probability of an inflation, okay, and let's say any event, let's say recession. So if, as an analyst, if I want to find what is the probability of inflation and recession, I will simply take their individual probabilities and I will multiply them. I will just join them together. And if I join, okay, let's say this is A and this is B. So where they join, okay, that is going to be my joint probability. Okay, this area. So that's my joint probability. Now, this is inflation, this is recession. So take their individual probabilities, multiply, you get your joint probability. That joint probabilities, these all events or the different types of probabilities that we will see, it will help us eventually. For example, joint probabilities will help you in the conditional probability, and conditional probability is something that you would see in the Bayes rule. Okay, so let's just understand the joint probabilities. So as I said, event A and B, they both occur together. When they have both, you have to multiply. Now remember, this is also known as a multiplication rule. Okay, what about mutually exclusive events? Let's say inflation and maybe GDP increase. Let's say we have these two events, A and B. They never occur together. So can you find a probability of inflation and GDP together? Can you find the joint probability if they're mutually exclusive? No, you cannot find that. If this is inflation, if this is GDP, as you can see, they do not join each other. So the joint probability of both of them will be 0. Okay, what about union of events, also known as the addition rule? Now, union of events, it means that either A happens or B happens. For example, either inflation happens or GDP will go up. Either of these two things happen. Okay, so when we have such a scenario, if as an analyst, if you want to find such a case, then all I need to do is I need to add up the entire inflation probability. Let's say we have this as 40%, and I need to add the B probability. Let's just say this entire B, let's say, which is 60%, or maybe let's say 55%. Okay, minus the probability of A and B together. Now, why I'm deducting this joint probability of A and B? Because as you can see, I have already calculated here. So if I just draw it like this, now you can see that there are two greens, once this time and once this time. So I have double added together when I added the individual probabilities. So it's important I take out once, okay, one joint probability. I need to take it out so that that thing is not added up. Okay, so that's a double addition that we do. So we need to take it out. And that is why you would see that there's a negative or removal of the joint probability. Okay, so that's the union of events A and B. Whenever you see and, multiply. Whenever you see or, either A or B, plus, that's an addition rule. And when you add it, you need to take out the joint probability. All right. So unconditional probability is the single or standalone probability of an event, which is known as the unconditional probability. So as an example, the probability of a recession alone is the unconditional probability. The probability of inflation, okay, that's going to be the unconditional probability. There's nothing attached to it. But now let's just attach something to, let's say, inflation or recession. So here we have the conditional probability, which is the probability of event A happening given probability of event B has already occurred. As an example, when we register for the FRM exam, there is a condition. You either needs to have a passport or a driver's license, right? So given you have a passport, you can register for the exam. So there is a condition attached to it, right? So that is what conditional probability is all about. Okay, so given you have either a passport or a driver's license, what is the probability that you would register for the FRM exam? You can find that. And this is the formula that can help you find the answer. Okay, so let's just look at this thing visually. So let's say we have any event A, or maybe we can just say what is the probability that recession will happen given this bar is known as given. Maybe let's say the money supply, the money in the market has gone up. So what is the probability for that? Now, One thing is for sure, we know that the money supply has gone up in the market. So this is given to us. And we need to find what is the probability for a recession, given that this thing has happened. So if you look at this is recession and this is money supply increase. So this red circle has already happened. Okay, so what do we need is we need to find the other thing. So essentially this circle is something that we don't need because our sample space, okay, our sample space is just this much. So what is the probability of recession? Only this much. As you can see, this overall joining of this curve is something that you see. This is the only probability of a recession, this line over here. And that's how visually you can see that. So what is the formula? It's nothing. It's the probability of A and B, which is the joint probability, divided by the probability of B. Now, whatever that we have in the denominator, that's my sample space. So as you can see, we are already given that the money supply has gone up. That information is there. So that becomes a new sample space. And within this sample space, what do we have? The recession is only this much, which is the joint probability. So that's why we have in the numerator. Okay. Remember this thing on the exam, whatever is there after given, that is going to come in the denominator. So conditional probability, it's a very important thing and something that builds up while using the Bayes rule. All right, moving on to independent events. Now, independent and conditionally is not something that we really want to deep dive into these things. So independent events, two events, A and B, they are said to be independent when knowing one outcome does not affect the probability of the other outcome. Okay, so maybe you, as I said, that there is money supply, that's what we talked about in the last example, right? So A, the recession was pretty much dependent upon the money supply, right? But if I say that if money supply goes up and let's say a candidate passing the exam, there's no relationship between that. Whatever happens to money supply, that's not going to affect the passing criteria for FRM exam, right? So we can say that both these events are independent of each other. When the probability of the other outcome, it does not affect A. That's what we mean by independent events. What is conditionally independent events? If two events, okay, maybe we can say probability of A and maybe we can say the probability of B. If these two events, if they are conditional on a third event, let's say third event, maybe let's say C, let's bring up anything. And then we say that they are conditionally independent events. So conditionally independent is something that, you know, initially these two events, let's say probability A and B, they're dependent upon each other. They are dependent upon each other. And once we add another event, let's say C, then they both become independent of each other. And that's what we mean by conditionally independent events. So we added up a condition and now they are independent altogether. So that's what we mean by conditionally independent events. Okay, then we have the Bayes rule. Okay, so we need to understand this thing very well. This is a high probability question on the exam. Now, Bayes rule or Bayes theorem is based on the conditional probabilities concept. Same thought process is used over here as well. What is the usage of the Bayes rule? Well, it helps us to calculate the updated probability. This is very important. Okay, on the exam, you may not see something like, okay, calculate the Bayes rule. They'll tell you that, okay, something has happened. Now, what is the probability for that? So given something has happened, now what is the probability for that? So essentially, what is the updated or the new When you update something, you get something new, right? I mean, so what's the new probability based on other information or, other event has already happened? That's what we say in Bayes rule. And here we have the formula for that. Okay, so which is the probability of event B given A has happened. Okay, so we are given the information that A has already happened. So what is the probability of B now? What's the updated probability? So for this, it's the inverse probability multiplied by probability of B, okay, divided by the probability of A. As I said, whenever we have something as given, after given, this comes in the denominator. And over here in the numerator, we have two things, which is the inverse probability, okay, the inverse of this multiplied by unconditional probability of event B. What is B? The first one. Okay, so this is something that you need to know. Now, difference between the conditional probability and Bayes rule. See, to be honest, the Bayes rule, it can be, ideally they are one and the same only. Okay, they are one and the same. And this probability of B given A has happened, that can also be solved by using the joint probability of A and B. And what is thereafter, which is A, that comes in the denominator. So either ways on the exam, either ways, if you see this answer, the joint probabilities, actually there are two formulas for Bayes theorem. This is the first one and this is the second one. So using either of them, you can go ahead and you can solve the Bayes rule. So to answer your question, what is the difference between, or what's something, the conditional and the Bayes theorem? If you're given the conditional probabilities, go ahead, find that, you get the answer. It's not going to be as much complicated as we think or as we may, understand. It's very simple. If the joint probabilities are not given, then you know that, okay, if the inverse probability is given, then they're specifically talking about the Bayes rule. But nonetheless, Bayes rule can also be found with this thing. So now, what are the different types of questions that you could see on the Bayes rule? First is, maybe let's say you're given a probability matrix. Okay, you'll be given a probability matrix. It's going to be a table-like format. The probabilities are going to be given out to you. You just need to pick it up, plug it in the formula, and find the answer. That's one way that is most probably that you're going to be given out. The second type is maybe on the question set itself, there's going to be all the probabilities that you are given and you just need to plug into it. Thirdly, maybe you are not given the inverse probability and you need to find this probability first, something like that, and then you need to plug into the formula. Okay, so these are the two things, or maybe a binomial kind of a thing also may show up, which actually would take a lot of your time. So what I feel is the probability matrix is something that you might see on the exam day, or maybe on the question set itself. Okay, this probability matrix is something that we're going to be talking in the later chapters. But make sure that for the exam, you know the Bayes rule very, very well. Okay, all right, moving on to reading number 13, and that is a random variable. So random variable, let's look at the definitions first. A random variable is a variable whose value is unknown to us. So something we don't know, that is our random variable. What about the discrete random variable? So random variable, there are two types, discrete and continuous. So what is a discrete random variable? Random variable that can only take a countable number of possible outcomes is referred to as discrete random variables. Example, a credit score is something that we can count. The number of students that we can have in a class is a discrete random variable. What about a continuous random variable? Continuous, as the name suggests, it's a variable which can take up uncountable, something that you cannot measure or count. That's the continuous random variable. For example, height, you must be wondering, like, height is something I know my height, okay, it's 179 centimeters. Let's just say that. So you must be wondering, like, okay, it's 179, then what's the big deal? Because in reality, if you look at 179, it's not exactly at 179. It may be 179.02, or maybe it may be 179.025, or perhaps it may be even 0.2553. So this thing can actually go on and on and on and on. It goes up to infinity. Okay, so these kind of variables like height, weight, the stock returns in percentage, I can say that, okay, I got a return of 10% or 10.5%. But ideally, if I just write it down, okay, I can have n number of decimal values. And once I have that, I would say that, okay, that particular variable is a continuous random variable. Okay. All right. So the first learning objective is distinguish between the PMF, PDF, and the CDF. So when we have a discrete random variable, okay, we say that, okay, and if you want to find the probability for that, then probability mass function, it's a function that can help you to find the probabilities of those discrete random variables. Okay, so PMF, it's going to show you all the possible values. For example, if I toss a coin, either the heads will come or tails will come. Either these two things will happen, right? So the probabilities, let's say 0.5, 50% is for heads and 50% is for tails. So this visual diagram, okay, that can be a part of the probability mass function. I can also write it this way in notation, and statistical notation, that probability that X will be heads, that is equal to 50%. So this bigger, okay, capital letter X is the random variable, and the small x is the outcome that it can take. Fair enough. So probability mass function PMF is nothing. It's just for discrete random variable. We use it to identify the probabilities. Okay, it's a way of showing the probabilities for a random variable. Fair enough. What about probability density function? Now PDF, okay, probability density function, it helps you to calculate the probability of an outcome between two values. So for discrete, we said that, okay, there is this PMF. But what about a continuous random variable? Let's say I have a continuous random variable, something probability of a default in percentage, or something that just goes on to infinity. Then how can I find the probability of those event? Well, in that case, I'm going to be using the PDF, which is probability density function. Okay, there are many different types of PDF. Okay, I can have a distribution like this, or I can have a distribution like this as well. Okay, so this is a uniform continuous distribution. That means I can go ahead and I can find the values within this particular thing. Let's say this is X and this is Y. Can I find a specific or a single value? Let's say this, maybe we call this C. Can I find a single value or the probability of C? Can I find it if I know under the PDF, or if it's a continuous random variable? The answer would be 0. The reason is, in a continuous, as I said, it goes on to infinity. So in a continuous, it's going to go on infinity. If you say that 179 is your height, no, it's not your height. It's 179 point something, 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 so on and so forth. So at 179 exact, the probability is 0. So if I say that probability of my height to be being 180, let's just say that, that is going to be 0. But definitely I can say that, okay, the probability of my height may be, let's say, between 180 and maybe 182 centimeters. Yes. Now I can find that. Maybe I can write here 180 and this as 182. And then this is the range that I can find that. This is the probabilities that I can find that. Okay, so that's the probability density function. It helps you to get the probabilities for a continuous random variable. Okay, so the main point is this. Remember that in a continuous distribution, probability of any specific outcome is 0 because it's not possible. So that's why it's 0. What about us? Moving on to the cumulative distribution function, which is also known as CDF. Now, CDF, as the name suggests, it's a cumulative distribution function. So cumulatively, when you add up all the probabilities, how much is that when you add up? So that is what the CDF will answer that. Okay, as the name suggests, this shows the total probability of a random variable less than X. If I want to find a probability, maybe let's say this is X, and I want to find what is the total probability this random variable X can be less than or equal to this particular X. So I can just say that, okay, right, let's just say it as A. So I can write it here as A. So can I find that? Yes, I can just add up all these things and I can find that. Okay, for a continuous distribution, it's very easy. You just look at the table, find that, you get the answer. For a PMF, okay, for a, if you want to find the CDF for continuous distribution, it's very easy. Go to the tables, find it. For a discrete random variable, you just need to add up the individual probability. Let's say the probability when you roll a die is 1/6, right? And the probability for 2 is also 1/6. The probability for 3 is also 1/6, so on and so forth. CDF is for both discrete and continuous, right? That's correct. That's correct. CDF is both for continuous and the discrete random variable. So let's say that if I want to find the probability that X will be less than or equal to 2, I want to find the CDF for the random variable, which is going to be less than or equal to 2. So all I need to do is I need to add up this and this. 1/6 plus 1/6, that's going to be 2/6. That's 1/3. That's my CDF, or my cumulative probability that the X will be less than or equal to 2. Okay, so CDF is nothing but it gives you a full picture overview, okay, a cumulative overview of the probabilities that you are interested to find. Note one thing, it's always denoted as capital letter F, okay, F of X. And on the other hand, the other two that we just saw, that is the small f of X. Okay, so that's just one difference that you should know for the exam. All right, now let's just talk about the mathematical expectations. Okay, so expectation, as I said, it's something that we are taking the average, but it's not just the average, it's the weighted average of all the possible outcomes and their associated probabilities. Okay, so here, if we look at this particular formula, this E of X, that is the expectations of the random variable X, that is equal to the probability of X multiplied by the possibility or the weight of Xi. Okay, so this is the weight and this is the probability. So for example, if I'm given two events, A and B, and I know the probability of event A is, let's say, 40%, and the probability of event B is, let's say, 20%. And if I'm given the weight as well, or the respective the respective weights as well, and the associated probabilities or anything like that, then all I need is, let's say the weight is 0.2 and here we have 0.3. So all I need to do is, if I want to find the average or the expected value of X, I just need to have the probability of A multiplied by weight, which is 0.2, plus the probability of B multiplied by the weight, which is 0.3. Okay, so I can just write up these things: 40 into 0.2 plus 20 into 0.3. 3. So once I solve this thing, I will have the expected value of the random variable. Okay, so expected value, it's simplistically, it's the weighted average of all the possible outcomes. Okay, as you can see here, we just multiply the outcome and its probability. Okay, the probability of having 1 when we roll a dice, what is the probability for that? 1 by 6. The outcome is 1, right? So we can just have all the probabilities for each of these things in the expected value. All right, that's the thing about the expected value that you should know. Okay, what about the 4 common population moments? Now moments, okay, they actually describe the features of a random variable. Okay, when you have a data, when you have the data of the random variable, what can you make out of that particular data? What can you understand from that, you know, having a visual look, and how can you describe your data very well? So you need some things or some parameters, and these are known as the moments. So the very first moment that we have is the mean. Okay, so mean, it measures the average or location of a random variable. The expectations that we saw, it's nothing but the mean or the average. Okay, so symbolically, this is how it looks like. The mu, it's known as mu, sorry, that's mu, that is equal to the expected value of x, or the expectations of the random variable x. So that is the same thing. How do you get the expected value of x? Probability multiplied by outcome plus probability multiplied by outcome. Add it up, that's the expected value of x. So that is my mean basically, and that's a first moment. What about the second moment? And that is a variance. Variance is defined as the expected value of the difference between the variable and its mean, and you take a square of it. Have a look at the formula. The variance is the x, which is the variable that we have, the random variable, minus the mean, and you take a square of it, and you take the expectations of that, the average of all these things. That is the variance. If I have to draw it diagrammatically, okay, if let's say this is my distribution, then in the center, that's going to be my mu, or the average, or the mean, and the variance is like how dispersed my data is, how spread out my observations are. That is what variance is all about. How can you calculate that? You take x, which is the value, let's say the random variable, any value, minus the average value, which is the mu, you square it, and you get your variance. If you have multiple values, then this is for, like, let's say, x1, then for x2, it's going to be x2 minus mu, the square it. If you have x3, another value of x, minus mu, square it. You add up all these things, and you will have your variance. Fair enough? Basically, variance, it tells you how spread out or how dispersed your data values are. That's what variance help you. What about the third moment? So essentially, we're describing our data, right? We're taking a center, the average value. We are seeing, okay, how dispersed our data is. And then we can also have something which is known as skewness, measure of shape of the distribution. And ideally, it measures for outliers or observations very far away from the mean. So when I showed you this distributions, okay, and I said that, okay, and I said that variance is, it tells you how far away or, the dispersed your data is. But skewness, it looks for an outlier. Let's say if your data is maybe at this point here, or maybe at this point here. So your entire distribution is going to be skewed towards these values. Okay, so it looks for an outlier. If you have a data around here, then your distribution will be stretched out. And that is what skewness is all about. Okay. Looking at this thing diagrammatically, what we need to understand is there are three types of skewness. Okay. One is the negative skewed. The other one is the positive skewed. And the third one is essentially the normal distribution, whereas there is zero skewness, no skewness at all. So one can be positive, negative, and no skewness. Now, what is this negative and the positive skewness? So if you have a look out here, as you can see, if I have my data like this, these are my positive values, these are my negative values. So if I have a negative skewed data, then all my values are clustered in the tails over here. There's a lot of negative values in my data, and that's problematic. That's problematic. That's not a good situation. On the other hand, if I look at a positive skewed data, my values are to the extreme of these positive numbers. So that's a good sign actually. If I ever wish to have skewed data, I would want to have positive skewed, because a lot of positive values in the tails, and that is good. On the other hand, the negative is something that I would not wish. Okay, so that's something that describes your data. Is it skewed, not skewed, positive, negative? What is it? That's something that can be shown with the help of skewness. Now, skewness, there's a formula for it. And if you look at that, the value, the random variable, minus the mu to the power 3. Why 3? Because it's the third moment. And if you want to standardize it, standardize means you make it more, just like correlation is standardized. Okay, if you want to do that, then we have the standard deviation cubed. That's the formula for skewness. Just like in variance, what we do is we take the standardization by taking the square root of this, and we get the standard deviation. Similarly, if you want to standardize, I can use this standard deviation cube. Fair enough. That is the formula for skewness. What about kurtosis? Kurtosis standard is the fourth moment that we have, and it also tells you about the data. Now, what does kurtosis tells you? It tells you whether the distribution is more or less peaked than the normal distribution. Okay, so we are comparing a normal distribution. So if you see this one, it's a normal distribution, and the red one that we have over here, kurtosis in the data, and especially the red ones, the tails are very fat. That means a lot of data there in the tails. If they are there in the positive tails, that's a beautiful situation. That's a very good situation. But if they are in the negative tails, then that's a bad situation. So kurtosis, it tells you how fat or how much data is in the tails. If you want to find that, kurtosis is the measure that you can calculate. Okay, how do you calculate it? X minus mu 4 to the power 4. Why? Because it's a fourth moment that we have. And if you want to standardize it, the standard deviation to the power 4. That's all that you need to know for the kurtosis. Okay, so kurtosis actually looks at outliers in either direction in a distribution. Over here, where are the extreme outcomes? That's what it says in the kurtosis. Now, the point that we need to remember, rather, I would say that normal distribution has a kurtosis of 3. So this one has a kurtosis of 3. Remember this for the exam. Normal distribution, the kurtosis is 3. And we keep this 3 as the base, and we see that, okay, it's a excess kurtosis, so on and so forth. But normal distribution has kurtosis of 3. All right, moving on to the quantile function and the quantile based estimators. So talking about the quantile functions, which is denoted as QA, quantile functions is the inverse of the CDF. Okay, so we talked about the cumulative distribution function, which gives us the value that the random variable X will be less than or equal to any specific value, which is the outcome is X. So if I want to find the inverse of the CDF, I can find the quantile function. So ideally, what happens in the CDF, okay? In the CDF, I am not given this probability. I'm just given a value of 2 and I write it like this. I say that, okay, what is the probability that the random variable X will be less than or equal to 2? Then I go to the Z table, I find the value and I say that, okay, it's 30%. This is the probability, or 30% is the probability that the random variable will be, or random variable X will be less than or equal to 2. Okay, so what I found is the probabilities. Now you're given the value, okay, you're given the probability in quantile function, you're given the probability which is 30%, and you're trying to find the value. Okay, so in quantile function, it's going to look something like this. Quantile function, you are given the probability that, okay, we have a probability Q30. What is the value over here? So again, you go to the table, the Z table, you see where is 30% and what is the value associated to it? Okay, it's 2. Then you say that, okay, it's 2. Then you say that, okay, Q30, the value is 2. That is what quantile function is. It is just the inverse of the CDF. Fair enough? You are given one and you need to find the other one. So essentially, quantiles, if I have to describe it for you, quantile is something that divides the distribution into certain lines. Okay. Under this quantile, we have something known as percentiles. Right? Percentiles is something that will divide this distribution into 100 equal parts. That is going to be percentiles. Okay. Then we can also have deciles, so on and so forth. But for now, the two major interests that the curriculum has asked is the median and the interquartile range. So what is median? Median divides the series into two equal halves. Okay, so if I just divide this entire distribution, okay, let's say if I just divide this distribution into two parts, then I will say that, okay, this is my median. This is my first part and this is my second, the other part of the distribution. Okay, so that's my median. It does its job by dividing this entire distribution into two equal parts. That's all that it does. What about the interquartile range? As it says, the interquartile range is the difference. Interquartile means you divide the distribution into 4 equal parts. Okay, so let's just say that I can divide this thing into 4 parts. So this is my first, second, third, and this is my fourth part, right? So the interquartile, that means out of these quartiles that we have, the inter, that means within a median itself. Okay, if I just have to show you, if I just, so within, this is 50% of the data, the median has divided 50% of the data. So what is the interquartile now? It's over here. This one, the quarter first you can say that, or maybe quarter 2 is something that you can say that, quarter 2. Similarly, for the other distribution, I can divide it and I can pick up this particular portion, okay, which is quarter 3. I can go ahead and I can do that. And essentially the interquartile range, it helps you to find the values within this median, okay, somewhere around the mean you're trying to find in the middle 50%. As you can see, if this is 25%, this is 25%, this is 25%, this is 25%. So essentially all I'm trying to do is I'm trying to find the values within this middle 50% of the data. That is what the job of interquartile range is. Okay, so interquartile range, it's the upper and lower value of the outcomes, this upper value and the lower value of the outcome of a random variable that include the middle 50% of its probability distribution. So in the middle, I have this 50% of the data in the middle out here. So basically I leave out this portion and this portion. That's what the interquartile range tells you. If you have a data and if you want to find, okay, what is the interquartile range, you go ahead, you find from this point up until this point, and then you say that, okay, my data is very much clustered around the mean, so on and so forth. That's the conclusions that you can actually draw from the interquartile range, and that's their overall use. Okay. Then after moving on from the interquartile range, we move on to the effect of a linear transformation of a random variable. Now, linear transformation, so the effect of a linear transformation of a random variable. Now, what exactly we are doing is we are taking a random variable. Let's say we have a random variable y and another random variable x, and we are just making changes to this x. Okay, so let's say we have two constant value, which is a and b. We are just making a change on this a and b, and we are trying to find, okay, what is a value or what is a transformation on this x, or sorry, y. Okay, so that's what linear transformation does. You have x variable, you have y variable, you make some changes to the x variable and you try to see the effect on y. That's what linear transformation means. Okay, now this a is known as the location parameter and this b is known as scale parameter. So scale means you see this b, you're multiplying b by x. So that's why when we have it multiply, that means we are scaling it, we are expanding it. And the location, it's like shifting things together. That's what we mean by a and b. So look at this particular diagram over here. So here the x is shifted by a. Okay, x is shifted by a. So this is my x, this is my new random variable, which is y. So once I add, let's say a is, let's say 2, okay, plus b and x. So once I add anything to this random variable x, if I add it, you can see the effect. Okay, and by just having a look at this, this is my first, the mean of x, the second mu, which is the mean of y. As you can see, the mean is shifted to this side, right? So I can say that the mean of y is shifted, or it is affected by the value of a. Can I say that? Yes, I can say that. Just have a look. Don't you think so that this mu has been shifted to this side? Yes. By how much? By a. Now we don't have to calculate by how much. We just need to understand the effect of a linear transformation. So when we transform x with these two variables, what is the effect on y? That's exactly what we need to find. So what is the effect of a linear transformation on a mean? Yes, it is affected by the location parameter, which is A. So it's affected, it's been shifted. The mean has been moved from here to the next point. What about the variance when we add a constant to X? What happens on the variance? On the variance, scale A, it does not affect. Okay, this it has to be location. A is a location. So as you can see, the location, the variance is pretty much the same. How do you measure the variance? If this is the earlier variance and this blue one, the variance is this. Don't you think so? This and this, they are both the same. Yes, it is the same. So when you shift the X by A, the variance is not affected at all. Fair enough. What about the skewness? The skewness, as you can see, okay, there's no effect. There's nothing, it's been skewed or anything like that. Kurtosis, no effect at all. Okay, it's not been scaled up, down, something like that. So that's something that we need to know. Now, if I just go ahead and if I just scale the X, now if I add this constant B and if I multiply this B to the X, what is the effect on Y? Let's see that. So this is my original distribution and this is my X random variable. Now let's see the effect on Y. Okay, so as you can see, this was my mean. Okay, this was my mean, and now my mean is almost like doubled 2 times. So when I multiply this independent variable by B, my mean is affected by the scale parameter. It's almost like doubled. It's been so stretched out, right? So the mean is affected. Yes. By how much? By the scale parameter, or rather I can say B squared. Okay, that's the mean. That's the effect on the mean. What about on the variance? As observed, scale A does not affect. So the variance, this thing is not affected to the variance. Over here, this is my original variance. And now the variance is almost, it's gone up by the B squared. The variance of Y will be the B squared multiplied by the variance of X. So as you can see, the variance of X, it has gone up by how much? By almost double, which is B squared. Okay, what about skewness? Ideally, no effect. But if this B, if it's a negative value, if this becomes a negative value, okay, then if this is the case, when the B is negative, the negative multiplied by X, it's going to be negative. So the skewness will be, the skewness of Y will just be a negative answer, nothing else. Ideally, there's no effect on the skewness, but the answer, if B is less than 0 means it's a negative. So if this is the negative case, the answer will be negative. That's it. Okay, what about kurtosis? No effect on the kurtosis at all. Okay, so that's all that you need to understand for the linear transformation. Okay, the mean is affected, yes, by both the location and the scale parameter. What about the variance? This is, as I said, it's location. So as observed, location, when you shift the mean, okay, there's no effect on the variance. The blue one and the other one, the variance is the same. Fair enough. What about the other? When you scale it, when you multiply it, the variance actually doubles up. It's doubled. It's by the square of B. Skewness, no effect. Kurtosis, no effect. Only when the B is negative, then we will have this thing over here. Fair enough. So that is something we have in the linear transformation. All right, so let's start with reading number 14, and that's common univariate random variable. So again, a discussion on the random variable that is still going on, and we are talking about the univariate. That means one random variable. Okay, and we're going to be checking about the distributions or the different shapes that the random variables can take. All right, so let's look at the first learning objective. Distinguish the key properties and identify the common occurrences of the distributions. Now, the distributions, there are a lot of distributions, but for the purposes of this particular chapter, we're going to just looking at 9 or 10. Okay, let's look at the definition. So discrete random variable is something that we've already seen. That's something that you can count. Okay, that's discrete random variable. So a distribution, if we create from a discrete random variable, we say that, okay, that's a discrete distribution. What about a continuous? These distributions take values in a specified range. We know for a fact that continuous, you cannot have a single value in a distribution. You always calculate within a particular range. All right, moving on to the distributions that we have. The first one is the Bernoulli random variable. Now, this is something which will help you in the other distribution, which is the binomial. So Bernoulli, just know the property. That's it. That's all that you need to know. The application of Bernoulli is used in the binomial distribution. So what is a Bernoulli random variable? A random variable will be classified as a Bernoulli random variable if the random variable can only take two possible values. Okay, when you toss a coin, there are only two possible values, either heads or tails. So we can say that, okay, a coin toss is a Bernoulli random variable. What about the default of a bond? We can say that the bond can either default or it can survive. Only two possible outcomes, right? A company can either survive or file for bankruptcy. So when we have just two possible outcomes, we classify them as a Bernoulli random variable. Okay, and here the notation is like this. Okay, so there are some notations that you should know. Now, this one is referred to as probability of success, and the 0 is referred to as a probability of failure. That is just the notation. Okay, so 1 means success. That means if you toss a coin and you wanted to find heads, so if when you toss it, if the heads comes, then we say that, okay, it's a success. That means it's a 1. If tail comes, then it's a failure. That means 0. Okay, so these are the notations. Now, the main thing that you need to understand from the Bernoulli is that this is how the PMF actually looks like visually. But main thing is the formula that we have, which is the mean and the variance. Okay, the mean is the probability, P is the probability of success. So if a corporate bond, if defaulting, the probability of default is, let's say, 0.7, then that is going to be the mean or the average, or which is the probability of success, which is P. Okay, so whatever the P is, that is going to be the mean. What about the variance? Variance is P, okay, the probability of success multiplied by the 1 minus P is what? 1 minus P is the probability of failure. Because we just have two outcomes. If success is 60%, failure has to be 40%, right? So that's what we have in the Bernoulli. Now, these are just the common notations that you will see somewhere else. Okay, so just make sure that you go through it. P is the probability of success. This lambda, it's the average values which you will use in the Poisson distribution. N is the number of trials or the number of things that we have. Okay, now let's look at the second distribution, which is a binomial. Now, binomial is a collection of Bernoulli random variables. So Bernoulli is just for one coin toss. But if you do it multiple times, the distribution that you end up with, okay, this particular distribution, that will be actually a binomial distribution. Okay, moving on from the coin toss example, let's say if I have maybe two bonds, not just one now, I have two bonds, and the probability of one bond defaulting is this. The probability of the second bond defaulting is probably no default, and the probability that both the two bonds they default, that's this probability. So for a bond, the outcome is the same. It's either default, no default. But when you have multiple bonds, then it's going to follow a binomial distribution, or maybe multiple loans for a bank. Okay, so when it's discrete, when there are few in numbers, that's something that you can follow a binomial distribution. And what is the binomial distribution actually used for? It's used for finding the exact number of success, the exact number of times, the exactly how can, if you toss a coin or if you just roll a dice, what is the probability that exactly this thing will happen, exactly that thing will happen? So when you have something like that, we use the binomial distribution. Okay, and let me tell you, this Bernoulli, binomial, and the Poisson, these three distributions that we have in the book, they are all discrete random variables. So random variable which is discrete in nature will take either Bernoulli binomial or the Poisson distribution. Fair enough. And as you can see from the diagram, the bond default or any other thing can take on specific values, which is the speciality of the discrete random variable. Just hold on. Okay. I think this is fine. So as I said, this is used for this. What about the formula? If you want to find the exact number of success, how can you find it? Well, there is a formula for this, and this is something that you need to remember. Okay, make sure that you remember this for the exam. Okay, this formula. So the probability to find the exact number of success, that is equal to the n factorial, n minus x multiplied by x factorial. So basically, if you want to find probability that x is equal to, when you roll a dice, x is equal to 5, exactly it should land upon 5, you need to know that, okay, in how many ways you can do that. So there are like, how many trials, the n is the number of trials. So how many trials are you doing it? Are you doing it 5 times, 4 times, 3 times? So you need to define your n. Okay, then n minus x, x is something that you want, which is 5. So n minus 5, then multiplied by x factorial. So this is also factorial. So x factorial is something which is the 5 factorial, something that you want. Okay, then multiplied by the probability of, this is p is the probability of success to the power x, 1 minus p to the power n minus x. Okay, we'll take one little example on demonstrating this thing. Okay, what about a mean? If you have a binomial distribution and the question says that, okay, find the mean for it, the mean is the number, the n, multiplied by the probability of success. The same like the p, we over here we just have n. See, because as I said, binomial is a collection of Bernoulli. So the mean and the variance, they are pretty much the same. Okay, we are repeating n times. That's why we have this n over here. So that's the mean and variance of the Bernoulli and the binomial distribution. What about a Poisson distribution? When do we use this kind of a distribution? A Poisson distribution is often used to model the occurrence of events over some period of time, provided, okay, make sure that you know it, given some average or expected values lambda. So in the question itself, you'll be given an average value of something that is happening, and then you need to find, okay, how many times it's gonna, it's going to happen, or exactly at what, how many times it's going to be happening. So that is something that you want to find. And that's something when you use the Poisson distribution, given expected or the average value, which is the lambda. That is when you use the Poisson distribution. Okay. Then it's used for finding like how many number of defaults that may happen in a bond portfolio. Let's say I have a bond portfolio and I want to find how many bonds will default. I am an analyst. I have maybe 10, 20 portfolio of maybe 10, 20 bonds that I have. And I wish to find in a particular time frame, how many bonds will default, so that I can use the Poisson distribution and I can find that particular answer. Provided I'm given some average defaults. Okay. Similarly, we can also use the Poisson distribution, and this is something that you would see in your operational risk chapter as well, is that how many operational losses a company will face. I look at last year and I see that, okay, I have faced maybe 4 operational risk losses. There were like 4 losses on average in the last year. So using that average data, I can create a Poisson distribution and I can find that, okay, how many losses, the operational risk losses, will I face this year? So, okay, so that's something that I can do with the Poisson distribution. So let's just look quickly at the example. Okay, and the formula for the Poisson distribution to find X success given some average values, you need to remember this particular formula, okay, which is the lambda, which is the average. Okay, this is the average multiplied by e to the power negative lambda, this negative average. And over here we have the X, which is something that we want to find, divided by X factorial. You use this formula and you get your X success, whatever that you need actually, using the Poisson distribution. Let's look at these 2 examples. Okay, so on average, let's say 5 bond defaults, they happen every year. Okay, you are managing a portfolio and you notice that 5 bonds, they default every single year. So this is the average. So once you hear this thing average, it clicks, okay, that it's a Poisson distribution. Then what is the probability that 3 bonds will default in the next period? Now you want to find the probability that 3 bonds default, probability that X is equal to 3. That's something that you want to find. And these are the questions that you would see on the exam. So what do you need? You have your average. Yes, the lambda is 5. Okay, replace, just use this particular formula. Okay, so I can, the lambda is 5 to the power X. X is something that 3 multiplied by E to the negative lambda is 5 divided by X factorial, which is 3 factorial. Once you solve this entire formula, you will have the answer, which is the probability that exactly 3 bonds will default in the next period. Okay. And then what is the average default? If this is the question, what is the average default? The average is already 5, which is the mean. Over here, it's lambda. The variance, it's also lambda. Same, 5. No variation at all. Okay. So only thing, make sure that you do remember this formula for the exam. Let's take the second one. Assume we have 4 bonds now, or maybe 4 customers, 4 loans, whatever that you want to say. Okay. And an analyst wants to find the probability that exactly 3 bonds will default. What exactly you want? 3. So put it out here. Probability that X is equal to 3. With probability of each bond defaulting is 10%. Now there is no average bonds here. So now you know that, okay, it's a discrete number because we want to find the probability to be exactly 3. So we need to use the binomial distribution. So probability that exactly 3 bonds will default, okay, that is going to be this particular formula. So what is n? N is the number of things that we have. N is equal to 4. What is x? X is something that you want to find exactly 3. So that x is equal to 3. Is there any probability? Do we need the probability? Yes, we do need it. And it's going to be mentioned on the exam. The probability of default, the P is 10%, which is 0.1. Now just plug in the formula and you have your answer. Okay, so as an example, all we can do is probability that exactly 3 bonds will default, that is equal to n is what? 4 factorial. Then n minus x is 1 factorial, and then x is 3 factorial. Multiplied by probability is 0. Probability of success to the power x. X is what? 3. Multiplied by probability of failure, that this is success, this is failure, right? 1 minus p is 0.9. 1 minus this thing to the power n minus x. What is n? And 4 minus 3, that's 1. So once I solve this thing, 4 into this 4 factorial, you just take this thing. Okay, you can use a calculator, you can solve it. 1 factorial is 1. 3 into 2 into 1. So this is gone. So the answer that remains is 4. Okay, so that's going to be 4 into this 0.1 times 3 into 0.9 times 1. So once you solve this thing, you will have your probability that x will default. There's going to be 3 defaults, exactly 3 defaults given this sort of data. Okay, so it's very simplistic. Do not get confused with these distributions. They are very simple. All you need to do is that you need to remember these formulas and just look at the question. Everything is there. You can easily solve these questions if they occur on the exam. Okay, so make sure that you are thoroughly with that. Okay, now from the discrete, we are moving on to the continuous distribution types. So the very first continuous distribution is the uniform, okay, continuous uniform distribution. So it's a distribution where each outcome is equally likely to occur. So maybe a probability of default, if it's continuous and each bond or each loan has a, equal probability of default or something like that, then we say that, okay, it's a continuous uniform distribution. Similarly, the probability of a rolling a dice is 1/6. So 1/6 for all the things. But remember, we are doing continuous. Okay, so that means having a single value, the probability of x is equal to a single value, let's say 2, that's going to be 0 because it's a continuous. You cannot have a single value. Okay, so the probability, having a look at this thing, this yellow rectangle is a continuous uniform distribution. It's bounded by A and B. That means, above this B, there's not going to be any probability, and below this A, there's not going to be any probability. All the probabilities is going to be within this yellow rectangle. Fair enough. And if you want to find the probability, as I said, it's always going to be within a range. In a continuous, it's always going to be within a range. So let's say A is 10, this B is, let's say, 20, and this X1 is, let's say, 15, and this X2 is, let's say, 18. And you want to find the probability within this. This is something that you want to find within a range, like between 15 and 18. What is the probability for that? Well, it's very simple. X2 minus X1, that is 18 minus 15. You take the difference divided by the overall probability that we have, 20 minus 10. You solve this thing, 3 over 10, that's going to be 30%. So this probability that the random variable will be between 15 and 18 is going to be 30%. A very simple, out of all the distributions, this is a very simplistic one. All we are doing is using this particular thing, and we can find any value within this range, even though it's a continuous distribution. Okay, so talking about the mean and the variance, mean, as you can see, it's very simple. It's the simple average. I mean, of course, if this entire thing is 100%, if you divide it in the middle, then it's going to be the mean or the mu, right? So formally, it's a plus b divided by 2. That's this value divided by 2, and you get your center point, which is the mean. What about the variance? Variance is b minus a square, this minus this, square it, divided by 12. Okay, this is something that is there for variance. Okay, the more important formula is this is something that you need to know for the exam. All right, so that's the continuous uniform distribution. What about the normal distribution? Now it's a very crucial something that you would see in finance and throughout the FRM curriculum a lot is the normal distribution. Also, we call this as a Gaussian distribution. Now, when we talk about normal distribution, if you look at this distribution, this shape, it's a bell kind of a shape. It is symmetrical. That means by just having a look, visual look, I can say that yes, it's very identical. It's symmetrical. Whatever that I have here is something that I have here as well, right? So it's symmetrical in shape. The mean, median, and mode are all equal. So if I just take this center point of this distribution, that's where I will have my mean, which is expected value of x is mean. I will also have my median and my mode, because mode is the, the top value, which is this. The median is divides into two parts. So that's the median as well. So that's one thing that we have for normal distribution. The mean, median, and mode are all equal. The skewness is 0. As you can see, there is no skewness left, right. No, there's no skewness at all. So that's a 0 skewness. And the kurtosis is 3. Okay, remember this for the exam. A normal distribution has a kurtosis value of 3. And then by looking at this normal distribution, we say that, okay, when we look at the kurtosis, we say that, okay, it's above, less. That's different topic. But for this, remember kurtosis is equal to 3. Now, let's talk about the first thing that we have over here. It's a first normal distribution. Now, the best thing about normal distribution is that most of your data, okay, when you work in finance, when you have data, most of the data, they will look like a normal distribution. So that really helps you as an analyst. It really helps us to understand our data in a much better way. Okay, so if my data is like this, by just having a look at it, I can say that, okay, 50% of my values is to the left of the mean. This is mean, right? And 50% of my data is to the right of my mean, the average. I can do that. Moreover, by looking at the normal distribution, there are some established features, which is like this: within one standard deviations away, like this, one standard deviation away from the mean, there's going to be 68% of the data. So if I'm doing a research, I can say that yes, 68% of the data is within one standard deviation from the mean. So I can conclude certain things. Moreover, I can say that within 2 standard deviations away from the mean, I have almost 95% of my data values. That's also a good thing. So this establishment, okay, this within one standard deviation, within 2 standards, it's known as confidence intervals. Okay, that's my confidence interval. And basically I've taken an interval of within 1 standard deviations, within 2 standard deviations away, and so on and so forth. So it's a good thing. If I have a data, it looks like a normal distribution. I can just go ahead and I can make some conclusions. Okay, let's try to do that for this particular data that we have as sales data. Let's say I'm looking at the sales of my company and I see that, okay, this $20 million is my mu, or the average. And then I want to make some conclusions that, okay, what is my sales? The average sales is $20 million. Okay, fair enough. Then how likely is it that the sale is going to be within one standard deviations, that is between 16 and let's say 25, whatever that number. So I can say that, okay, the probability is 68%. 68% of the times it's going to be between 16 and 28. I can say that by just having a look at this confidence interval. But now let's be more specific. Okay. And I want to find what is the probability that, okay, it's going, my sales is going to be $32 million and above. $32 million and above. I want to find that. So now this is a challenging part. I can use this, but it just gives me pretty much 68%, 95%, so on and so forth. But I want to be very specific. Okay, like I want to know what is the probability which is beyond 32. So in this case, what I need to do is I need to convert my sales data, which is a normally distributed, into something which is what we call as a standard normal distribution. Okay, so a standard normal distribution, once I convert this, the mean will be 0 and the standard deviations will be 1. So the difference is going to be 1 standard deviation. Over here we have 1 standard deviation, 1 standard deviation, so on and so forth. That's the benefit. Here we have a different standard deviations. 20 minus 24, that's 4 standard deviations. 16 minus 20 minus 16, that's -4, so on and so forth. So here the standard deviations is different. If you have another data, maybe revenue, other kind of data, any company data, the standard deviations will be different. So the best part about a standard normal distribution is the mean is always 0 and standard deviation is always going to be 1. Now, you must be wondering, like, what's the use of converting this thing? Well, if you have a standard normal distribution, any data, any probability or any value that you want to find under the curve, you can find that with the help of something which is what we call as a Z tables. You look at the Z tables and you can find any area under the curve. And that is the best part of converting a normal distributed into a standard normal distribution. Now, how do you do that? You use this particular formula, which is the Z value is something that you need to calculate. Okay, so that's X minus the mu divided by the standard deviation. So let's say the X is what? X is, let's say, any value. Let's say I want to find above 32. That was something that I wanted to find, right? So I can take the X as 32. This mu is the average. The average is the center point, which is 20. Standard deviation, as we calculated, it's 4 standard deviations. So once I solve this thing, okay, 12 divided by 4, okay, and that's going to be 3. So Z value is equal to 3. So I get my Z value, which is equal to 3. So after solving this thing, I've converted everything and I got a Z value over here for 3. Now, what do I need to find? I need to find the area over here, which is this one. So how do I find it? I'll go to the Z tables and I'll find where do I see this 3, and that's going to be my overall value. Okay, so let's just go to that. Okay, so all right, so this is the positive or the cumulative Z table that is going to be provided to you on the exam as well, and something that you will have. So you don't need to remember these probabilities. Everything is going to be provided on the exam. So now how do you look or how do you check on the Z table? So first thing to notice is this thing. As you can see, it's a cumulative positive table. All the values are positive. There are no negative values of possible that is here. Okay, and it's also known as a left tail probability. That means this blue thing, as you see here, is all that is there in the center. These centers are all the probabilities. Okay, now we wanted to find that, okay, how much was above 32, the probability that my X will be greater than 32. That's something that we wanted to find, right? So we calculated the Z value and it came to be 3. Now just look on the Z values over here, just look at the value of 3. Let's just check, where do we see 3? So it's not there actually, it's 2.9, but there is also a 3. For this example, let's just say that we calculated the Z value to be, let's say 2.95. Okay, let's just say that. So 2.95, I can search for 2.95. So 2.9 and then 5. Okay, this one, 2.9 and then this. Okay, so this is going to be, sorry, this one, 0.9984. So Z value for 2.95, looking at the table, it came to me that, okay, this is 2.9 and from this line, it's 0.9984. But this is giving me the value for this one, right? It's giving me the value for this one, because this table is meant to give you the values for the left side of the distribution, all the left side. Okay, but I wanted to find the right side, which is this one. I wanted to find the right side, but the table is showing me the left side. So it's very simple. How do you do it? Well, we know that the entire distribution is 100%. That is 1. So I can just take this value 1 minus 0.9984, and I can find maybe whatever the answer that I get, that is going to be my probability for the right side. Okay, so if you want to find the right side, just take 1 minus the value that you get. That's it. Okay, so this is simplistically how you go ahead and you find the value on the right side.
Sir, I have one question over here. Like, how we are going to identify that, they are asking for a right or a left side? Like you mentioned over here, right, that we will subtract 1 when the value will be asked of the right side.
So yeah, so this thing is something that you would see on the exam, and it's going to be mentioned as a left tail probability, or Z is less than. So this blue sign that you see here, this entire blue curve that's been shaded, okay, this means that all the Z values that you have, they are to the left. That means it's a left tail probability. So all the values, all these values, okay, inside the table that you see, all these values are to the left of the Z tables, or to the left of the distribution. That is what these things tell. So if you want to find this white region over here, you cannot find using this table. Why? Because there are no, I mean, all the probabilities are to the left, and you want to find to the probability to the right. Like for example, in our example, we wanted to find the probability to this side. This one we wanted to find, right? Probability X is greater than 32. Greater. That means 32, 33, 34, 35, so on and so forth. So we wanted to find the probability for that. But here we have a table which is giving me all the probabilities to the left of it, which is less than 32. But do you want to find less than 32? No. I want to find greater. This region I want to find. So if I have the probability from this table, I can find the probability which is less than 32 was 95%. But I wanted to find the greater. So of course it has to be 5%, right? This entire distribution is 100%. And if you find this region, okay, if you find this region to be 95%, so the other has to be 5%. So that's the reason why we take 1 minus 0.95. All right, so that's why we convert every data into a standard normal distribution, so that we can find any values that as an analyst we are interested in. All we need to do is we need to use this particular formula. Now, what are the benefits of standard normal distribution? Well, the first thing is that the mean is 0. The standard deviation is equal to 1. As I said, that's the standard property. And you can find any value under the standard normal distribution with the help of Z tables. And what are the steps for that? Well, first convert your normal distribution to the standard normal by using that Z formula. That's something that we have seen. Once you get your Z value, go to the Z table and search for the probabilities. Then make sure that the table provided on the exam will most likely be a positive cumulative, which is what we saw. But since it's a normal distribution, negative value probabilities will be equal to the positive value probabilities. That means if you want to find this region, no problems at all. Just find the positive one and replace the sign. That's it. Put a negative sign in front of it. That's it. Okay. That's the normal distribution, standard normal distribution, I would say. Now, moving on to the other distribution that we have, and that is the log normal distribution. Now, there are times that normal distribution cannot be used everywhere. For example, if you have a stock, let's say ABC company, if you're, taking the historical data of all the prices, do you think so it's going to follow a normal distribution wherein it's going to have negative values like maybe negative 70, negative 50, so on and so forth? Can any company or a stock price can take negative values? No. So at those times, normal distribution cannot be used. So an alternative is a log normal distribution. Okay, so when your X, all the numbers are a negative number, you can take a log of that using this thing, and you get a distribution which is what we call a log normal distribution. Okay, so what are the properties of log normal distribution? It always has positive values. So good. I mean, if you want to model your stock prices, we know that stock prices, they can take positive values. The lowest it can go is 0, not below that, right? And what about the log normal distribution? Second property, it's bounded by 0. As you can see from this particular thing, it's the max, the lowest value it can take is 0. And it's right skewed. That means this tail is going on and on to the right. So it's a right skewed distribution. What are the uses of log normal distribution? As I said, stock prices, that's a very first usage. Modeling the stock prices, because we know for a fact that stock prices cannot take negative values. Second thing, in your operational risk chapter, you would see that, okay, log normal distribution is used to understand or to find out how much is the risk loss, operational risk loss amount. How much is my amount? Okay, so that's when we use the log normal distribution. I've put this here so that when you go to that chapter, this thing, you're going to come back to this thing over here as well. So it's better that you know that, okay, if you want to model operational risk loss severity is something that you would see over there. Loss severity, how severe or how much you use a log normal distribution for that. Okay, and as it's a right skewed, that means the loss is how much? Maximum loss. What's the maximum loss? That's a log normal distribution. All right, moving on from log normal to something that we have, and that's the T distribution, the chi-squared, and the F distribution. Have a look at this particular table that I created. A T distribution, it's pretty much like a bell-shaped curve, similar to normal distribution. But remember, it's not exactly a normal distribution. The reason is that it has got a lot of fat tails. The tails are pretty much fat. And that is the difference between the T and the normal distribution. And all the distribution that you see in this line, T, chi-squared, F, they are used in hypothesis testing. Okay, but let's just go through it. So a T distribution, it has got a lot of fat tail. Let's look at the properties. It's similar to the normal distribution. Okay, fair enough. It has fat tails. Okay. It has degrees of freedom. Okay, now there's a concept of degrees of freedom, which is actually used in the hypothesis testing. But for now, do not get into the, if you don't know what that is, it's just a freedom that is allowed if we have 10 variables or 10 things. All let's say if there are like 10 people, 10 chair. Okay, 9 people out of those 10, 9 people have a choice to pick up the first chair, second chair, third, fourth, fifth, sixth, 7, 8, 9, 10. But the last person who's remaining, he doesn't have a choice. If all the chairs are gone, he's just left out with only one chair that is left. So he doesn't have a freedom at all. So with data as well, we use something which is known as degrees of freedom. And we say that, okay, if there are 10 people, 10 numbers, use 9 values, n minus 1. So if there are 10, the overall freedom is only to the 9 people, as I gave you the example of chair. So that's the degrees of freedom concept. Okay, so it's similar to normal distribution, has fat tails, has degrees of freedom, which is n minus 1. And as the degrees of freedom approaches, or as the degrees of freedom increases, as the n increases, the t distribution, it approaches to be a normal distribution. Okay, so if you just see this blue line here, it's got a pretty much fat tail over here, a lot of fat tails, because the degrees of freedom is dependent on n, right? So if the n is low, the degrees of freedom will be low. So as the degrees of freedom is low, it's going to be looking like this. But as the degrees of freedom goes up, it's going to look pretty much like a normal distribution. Okay, so that is something that you need to know, what degrees of freedom. And as the degrees of freedom increases, degrees of freedom means number increases, it's going to look pretty much like a normal distribution. What about a chi-squared distribution? Not very much talk in the overall FRM part 1, but it's used to test if variance of a normally distributed population is equal to some value. Okay, so it's used pretty much in hypothesis, but as I said, not very much used in the FRM level 1. So just know that, okay, it is used to test the variance of a population to some sort of a value. So variance of a population, maybe you're saying that, okay, it's equal to 20. You're saying that, okay, you have a population data and you're saying the variance of that data is going to be 20. That's your assumption. That's your hypothesis. So then you use the chi-squared distribution for that. But more important, what are the properties of chi-squared? It's again bounded by 0. It's asymmetrical in shape. As you can see, there is asymmetry, just like a log normal distribution. And it also approaches a normal distribution as degrees of freedom increases. As the data increases, degrees of freedom increases, the chi-square will look like a normal distribution. Fair enough. What about the F distribution? Now, this is something that you would see a lot in the hypothesis in the multiple regression chapter. Okay, so what is an F distribution? It's used to compare equality of two variances of two populations. When you have two population, let's say CFA candidates, FRM candidates, and you want to compare the variance of both these two different populations, then you use the F distribution for that. But moreover, this F distribution in FRM part 1, it's going to be used a lot in multiple regression hypothesis testing. That is the betas, all those betas coefficients that we have. We want to test that. Then we use the F distribution for that. Properties of F distribution: bounded by 0, yes. Right skewed, yes. Numerator has degrees of freedom. Denominator also has separate degrees of freedom. So this is a special thing. If you look at the formula of the F distribution, okay, the numerator, whatever we have in the numerator and whatever we have in the denominator, This will have its own degrees of freedom, and this will have its own degrees of freedom. So just like a Z table that we saw, we also have an F distribution table. And on the table, you will see numerator degrees of freedom, denominator degrees of freedom. We'll look this when we are doing the hypothesis testing. Okay, so that's what we have within these three distribution. Then we have something known as the exponential distribution. It's exponential is used to model the waiting times, that how long, if I go to a restaurant, how much will I have to wait? Okay, how much time will I have to wait for that? So that's using an exponential distribution. I can use that. Or also in talking about the finance example, it's like how much time it takes for a company to default. Let's say I've invested in a particular company and I want to find out how much time will that company take to default. I can use an exponential distribution for that. Or maybe if I want to find that, okay, a startup company has given a bond, how long or how much time will it take for that company to default, or for that bond issue to default? I can use an exponential distribution for that. Okay, so make sure that you just know that why do we use the exponential? That's all that you should know. Okay, moving on to the beta distribution. Again, this is something that you just need to know these two lines. That's it. This distribution can be used for modeling default probabilities and recovery rates. Okay, when you look at your credit risk data, if you want to find probabilities of default and so on and so forth, you can use a beta distribution for that. If you want to find recovery rates, a bank has given a loan to the borrower and the bank wants to find how much they can recover, they can use a beta distribution for that. Okay, so it's used in credit risk modeling. What about a final thing that we have, the final learning objective, and that is a mixture distributions. So here, two separate distributions are combined. Okay, let's say that you have a data, you have two distributions. Maybe this is something that is one, and this is something that you have two. So you can actually, you can mix it up, these two distributions, and you can form a better distribution, a final third one like this. Okay, that's going to be a mixture distribution, a combination of two distributions that we have seen so far. That's a mixture distribution. Let me tell you, there are almost like 100 different distributions that are available. So you can combine any one of them, and and you can get your, so that it fits your data very well. That's the overall objective. Now, mixture distribution, it contains elements of both parametric. Parametric means the mean and the variance, which is like a normal distribution, and non-parametric, which is like just the historical data that you take. Okay, so when you have a mixture distribution, it's going to have parametric as well as non-parametric. What is parametric? Like all the distribution that we have seen, the normal distribution, it has a mean, parameters, variance, which is another parameter. Non-parametric, like it can be historical data distributions. Okay, when you just have the historical, you just pull it up, that's it. However it looks like, your data, however it looks like, it doesn't make any difference. Okay, then the usage of mixture is that we can see, or we can actually change the skewness and kurtosis of our data with mixing of distribution. So if our data is very much skewed, we can change it when we mix the distribution. That's all that you need to know for mixture distributions. All right, so moving on to reading number 15, and that is the multivariate random variable. Now, first learning objective, explain how a probability matrix can be used to express a PMF, probability mass function. Well, let's look at the definitions first. A random variable is a variable which is value is unknown, and we're talking about a single one random variable now. But what if I have two random variables now? I call them a bivariate random variable. And if I want to call a single random variable, in statistical term, I say that, okay, it's a univariate. Okay, a single random variable, one random variable, it's called univariate. We will often come across univariate. So you should say that, okay, it's one thing only. Bivariate, that means two random variables. Multivariate, that means more than two random variables. And the entire chapter is about multivariate random variable. But remember, for this particular chapter, we are just sticking to the bivariate random variables. Okay, moving on from the definitions, let's just look at the probability matrix. Now, probability matrix has all the probabilities that can be associated of two or more discrete random variables. Okay, so it has listing, it's a table kind of a thing wherein you can see the probabilities of two or more random variables. In probability matrix, all the probabilities are positive, which is the property of probability, or it can be 0 and are less than or equal to 1. If you add up all the things, it's going to be max equal to 1, which is also property of probability. And the sum, when you add it up across all the probabilities for x and x2 equals 1. Once you add up all these things, it's going to equal 1. Have a look at this particular probability matrix. So let's just say that I have one random variable, which is the return on any particular company, any stock, ABC company, TCS, IBM, whatever. And I have the earnings of that particular company. Okay. The earnings, like how much they've earned, earnings data. Okay. Or ratings, anything that can be a second variable, second random variable. Now, a probability matrix, it's like a table format over here, wherein you have the stock return. Either you can have 3%, 0%, 3%, positive 3%. Then the earnings can be negative, it can be neutral, or you can earn a lot, which is positive. And then in the middle, we are given all these are the probabilities. Okay. And the negative, it's 1, the 0, and this 3. That's just a number that has been given. So by looking at this probability matrix, you see that once you add up all these probabilities, 40, 30, 30, it's going to be 100. Once you add up all these vertically, this horizontally as well, okay, that's 25, 5, 30, this 30, this 40, it's also going to be 100. So that's the good thing about a probability matrix. And this satisfies, this matrix, it satisfies. So essentially looking at the properties of probability matrix, it can be observed that probability matrix is similar to the PMF. PMF also used to give you the same information, right, in a table kind of a format. So which also conveys the same thing. So that's why we say that, okay, the PMF of a bivariate random variable, that is equal to the probability matrix, which is what the learning objective is all about. Now, let me just tell you one important thing. If you look at this thing over here, this notation. Now, in this particular chapter, you will see a lot of notations. But if you understand the overall high-level concept, you're good to go for the exam. And specifically for this revision, I would say that do not get into these things. Okay, do not get hung up on these notations. So this f of x1, x2, x1, x2, that is equal to probability of x1 is equal to x1. So it's something that it's very confusing. But this f of x1, f x2, it's actually the random variable. Okay, this f of x, sometimes you will see f of x, x1, then x, this is 1. So this f of x, it's nothing. It's also known as random variable. But we cannot write random variable. So in statistical format, it is just written to be f of x. So I can even remove this thing and it will not make much of a difference. That is just there to, some people get scared that, okay, what is this calculation, so on and so forth. But this overall thing, it's nothing. It's known as the random variable. Okay, so do not get hung up. Do not get scared by these notations. Okay, moving on to the marginal and conditional distribution of a discrete bivariate random variable. If you want to find marginal distribution for a two random variable, if you want to find conditional distribution of two random variables, how can you find that? Well, for that, we have this probability matrix that is given to us. Okay, and by just having a looking at this probability matrix, this entire thing that you see here, okay, inside the table, this thing is my joint probabilities. Remember joint probabilities? That's something that we saw in the first chapter. Okay, that's my joint probability of two things, x1, x2. And outside this thing over here, that is my marginal probability, which is what the learning objective asks us to compute. So if I wish to compute the marginal probability, let's say I want to, if it says that, okay, compute the marginal distribution of x1 to be -3%, the stock return to be 3%. Compute the marginal probability for that. No problem. So it's 25 plus 5, that's going to be 30%. So addition of this particular thing is going to be my marginal probability for the stock return to be -3%. Okay. What is the marginal probability for the earnings to be neutral? Well, it's simple. Just add up this entire column, this thing. 15 plus 10, 25, 25 plus 10, 30. 30% is my marginal probability. So for anything and everything, I can go ahead and I can calculate that. Okay. And that's what we have over here. What about a conditional distribution? As I said, conditional probability. Okay. First thing first, this entire one thing is known as a component. Okay. For each component, this thing is known as a component. This thing is known as a component. Similarly, this thing is known as a component. It's a component. Just a term that you should know. Now, conditional distribution, as I said, conditional probability is something that one information is given to you and then you need to find something else. Okay. A conditional distribution, it sums the probabilities of outcomes for each component conditional on the other component being a specific value. That means you're given some specific value of other component and you need to find what is being asked. So have a look at, we want to find that, okay, the conditional distribution for this random variable, which is less than equal to 1. Okay. So this x1, given that x2 has happened, it should be equal to 1. So that means we are given this -1 is something that is given to us. Okay. And we need to find this x1. So where is x1? Over here. And we are given only this negative data. So given this negative data, that means whatever is here, this x2 that you need to pick up. Okay. -1 is x2. So how to go about it? First thing first, whatever is there after given x2, you go here, the data is -1. So that's your only thing that is available to you. So I can do it. I can remove this thing because I don't need it. All I'm given is -1, which is something that I have selected over here. Okay. Now what do I need to find? I need to find the x values given that it's -1 earnings. Given that the earnings, the x2, okay, it's -1. The earnings is -1. X2 is -1. So now how do you find the X value? It sums the probability. Okay. So you take, now it's not going to be a simple 25 plus 15 plus 0. No, it's not going to be like that. It's going to be the marginal probability, sorry, the joint probability divided by the marginal probability for each component. That means this 25 divided by 40, that's going to be 62.5. That is my probability for the return having -3%. Similarly, for the next 0% return, I will use the joint probability divided by marginal probability. That is 15% divided by the marginal is 40. And then you get 37.5, which is for 0. Then similarly, for the third return, which is positive 3% return, it's going to be joint divided by marginal. The joint is 0 divided by 40. That's going to be 0, which is what I have for third value. Okay. So this is how my data would look like for the conditional distribution. Now it's not a single probability that we are finding. This thing is a distribution. It's a distribution for conditional data. Okay. Now, if I have like x1 given x2 is equal to maybe positive rating or maybe +1, then what do I mean by that? That means only this thing is given to you. This thing is irrelevant. I can delete this thing. It's irrelevant. That means I just need to use this data for these x1. Fair enough. That's all that we are doing, and we are to find this 62.5. We are taken the joint probability divided by marginal probability. That's it. That's how I can find the conditional distribution. Okay. Now there's a related topic which is 15H, the learning objective, and that says that compute the conditional expectation of a component of a bivariate random variable. That means first we need to compute the conditional distribution like this, and then we need to take the conditional expectation. What is expectation? Expectation is the average, weighted average, right? That's what we need to take with the conditional expectation. So first thing, if I want to find the conditional expectation, what do I need? I need to have a conditional distribution. So let's suppose we have already found this conditional distribution. So we have it, no problems. Then I just need to take the average of it. So the average is the value multiplied by probability. So this is what we have over here. The value multiplied by the probability, which is this one, plus the value, the second value multiplied by probability, plus the third value multiplied by the probability, third value multiplied by the probability. And then you get the, once you solve it, you get your conditional expectation of the returns given that earnings announcement is negative. So X2 given the earnings is negative, given the earnings is negative. What is the conditional distribution? We have solved it. And what is the conditional expectation? The average of these two things. Okay. So that's all that you need to understand for this thing. Make sure that you know what they are asking. If X2 is equal to -1, that means we are just looking at this particular thing. If this 40% marginal probability is not given, no worries, calculated. 15 plus 25 plus 0, that's 40. So then this divided by this divided by this divided by this, you get your answer and you have your distribution. Fair enough? That's all that you need to know. Okay, moving on to the expectation of a function. Now expectation, as I said, again, it's a average, right? Number multiplied by probability, number multiplied by probability, number multiplied by probability, add up, that's it. average, right? So expectation of a function is computed for a bivariate discrete random variable. So it's going to be like you're going to be given this kind of a table wherein you have one variable here, other variable here, and you're told that you want to find the expectation of a bivariate random function, which is it's like g x1 x2 g. This g is nothing, but in mathematical terms we say that it's a function, just like p x is equal to 3. So this probability, it's just written in a functional language, nothing else. Okay, similarly this g of x1 x2, it's g is just a function. So it's a probability weighted average of the function of the outcomes. How do you calculate it? It's very simple. Let's say that you want to, this is the data that you're given, and you want to find the average or the expectation of a bivariate random variable function. So it's very simple. You start with x1 power to the power x2 multiplied by the probability, and you just take the summation. Okay, so for example, x1, let's say the first thing is 3. x2 is what? 2 to the power 2 multiplied by the probability is 35%, 0.35, plus the second x1, which is 6 to the power, which is left out is, let's take the first one only, which is 2 multiplied by the probability is 15%. Plus, then we move on to the x, this 6, this 3, just a minute. So first I've taken this 3 to the power this one, 6 to the power this one. Then I'll take 3 to the power this, 3 to the power x2, probability is 20%, plus 6 to the power 4, probability is 0.30%. 6, 4, the probability is 30%. Once you add up all these things, once you solve and add up all this thing, you will get your expectation of a function. Okay, so the formula is this, something, use this formula. Once you read it next time, you can use this book and you can read it. So sum of all x1 to the power x2 multiplied by the probabilities, summation. Okay, always start from x1. So this to the power this to the power this, and then this to the power this to the power this multiplied by the probabilities. So that's the expectation function. It may show up on the exam as well. Okay, what about the covariance, and explain what it measures? Now variance is something that is the spread or the measure of dispersion. Okay, if you have something like mean is here, how far your data goes away from the mean, that is the variance. But that was for a single random variable, right? In this chapter, we are talking about multiple or multivariate random variables. So when we have two random variables, the variance, it becomes covariance, the variance between two things. Okay, so covariance is the same measure of spread, it tells you the same data, but for two random variables. Covariance, it measures how two variables move with each other. One goes up, other goes up or down. What is the effect on the other one? Okay, that effect you will get to know from the covariance, or the dependency between the two variables, how much they both are dependent upon each other. So that's what the covariance, that's the job of covariance. Looking at the formula of covariance, if I want to find the covariance between random variable 1 and random variable 2, I can use this particular formula and I can find it. Remember, what was the formula for variance? Variance was x minus the mu to the power squared, right? This was a formula for variance. But now here we have two variables, x1 and x2. So I can say that x minus the average of the expectation of x1, expectation of x is mu1, which is what we have, x1 minus this mu1 multiplied by x2 minus mu2. So same formula, multiply x minus mu2. That's it. That's the formula for covariance between two random variables. But oftentimes on the exam, you're going to be seeing something like a covariance matrix. Okay, so this is how the covariance matrix looks like, and this is the variance of the first random variable. This on the diagonally opposite, you have the second random variable variance, and on this side, this diagonally opposite, you have their covariance. Okay, covariance of 1 and 2. So that's how you will see the covariance on the exam. Okay, so this is if on a particular question the covariance is not given to you, look for a covariance metric. If this is also not given to you, that means you will have to use this formula to calculate, and it's simple: x1 minus mu1 multiplied by x2 minus mu2. Simple. That's the covariance formula. Now, covariance, it has its own limitations. Okay, covariance is between negative and positive infinity. Once you calculate these calculations, okay, you can get any random number, and that's not comparable as well. And moreover, it can go to positive. It just can go on and on and on and on. So that's not something very much reflective, and that's not something that is good. So another measure that we use, very often we use, is known as the correlation. Okay, they both measure linear relationship. If one goes up, the other also goes up. One goes down, the other comes up, down, whatever that is, between the co-movements over time. But correlation, the better thing about correlation is that it's standardized, and the values, they range between -1 to +1. Okay, you cannot have a value of 2, 3, 4, 5, 10, nothing like that. Once we talk about correlation, the correlation, the values is between negative to +1. And that's the better thing. And that's why we often use correlation a lot. Okay, the formula for calculating correlation for random variable 1 and random variable 2, that is equal to the covariance, this one, divided by standard deviation of 1, standard deviation of 2. Okay, and oftentimes on the exam, if it's not going to be like on the exam, you'll not see that, okay, calculate the covariance. No, even if they ask you to calculate the covariance, you might be given a correlation, you might be given this thing. So covariance is just algebraically, you can multiply both these things and you can get it. And then they'll ask you to calculate the third thing in the same question. Okay, so that's how they're going to be twisting this thing. But yes, very basics, covariance, you should know the formula, you should know the covariance matrix, and you should also know how to get your correlation from the covariance. You should know that. Okay, moving on to the effect of applying linear transformation on the covariance and correlation between two random variables. Now, linear transformation is something that we already saw in the second chapter. We said that, okay, there is this particular first random variable, let's say x1, and if we just move, if we just make a change, if we just add a, this constant, any number to random variable x1, then the distribution, it shifts, right? It goes a little bit away. Earlier, this was the mean, and now this is the new mean, right? So it moves away. So now, same thought process is what we need to understand for the effect of linear transformation on covariance and correlation. We're talking about the effect of linear transformation on covariance and correlation. So first effect, if we have this kind of a model, x2 is equal to a plus b x1, the first effect of a linear transformation on the covariance of two random variables is that the sign of b determines the correlation between the components. Okay, for example, let's just say that this B is, first thing, let's just say B is greater than 0. Let's say B is maybe 2. So then the correlation between this x1 and x2, the correlation between x1 and x2, that is going to be 1. See, as I said, the maximum value that the correlation can take is 1. So if the B is 2, 3, 4, 5, 6, whatever it is, it's going to be 1. What if this B is now, let's say, 0? What if this B is 0? Then this entire thing is 0. So then x2 will be equal to A. So x1 will have no effect, no correlation on x2. I can say that. Right? So the correlation will be 0 if B is 0. What if the correlation, if this B is now a negative number? Let's say negative 1. Let's just suppose, no, sorry. Let's just take negative 2, any number that you want. That means x2 is equal to A plus whatever x1 value is, it's going to take a negative value. Let's say negative 3. So then, of course, the x1, even if it goes up, it's going to take a negative value, and this thing will also come down. So if x1 goes up, the x2 will come down. Why? Because it's a negative relation. Because the B value is less than 0. It's negative. Okay. So that is the effect on the correlation between x1 and x2. That's the first effect of a linear transformation. What about the second effect of a linear transformation? The second is that scale of A has no effect on the variance. The scale of B changes in the variance by B square. Just let's go to that. Let's go to that thing. So when we were talking about this linear transformation of one random variable, we said that, okay, if you just, if you add up A to this X, if you add up A to the X, the mean is shifted. The mean, it's shifted. The blue one, it has shifted, but the variance is the same, right? If you see this thing and if you see this thing, the variance is pretty much the same. So we said that, okay, the A does not affect the variance, right? The location does not affect the variance. But if you scale it, if you add a B, if you multiply that to the X, if you scale it, then originally it was like this, but the new one is like, it's doubled. And we said that, okay, it's B squared. The new variance was doubled. Same thought process is something that we need to understand for this. Okay. So a second effect of linear transformation is that scale A does not affect the covariance or correlation at all. The scale of B, when you multiply this B, it's a multiplication term to the X, then it changes by the B square. Why square? Because it doubles. And that's why we have B squared over here. So that's the second linear transformation effect. What about a third effect now? A third effect of linear transformation on the covariance is that the scale, which is B, of covariance is determined by two variables B and D as follows. Let's suppose that we have this thing over here. Let's say the covariance is first, and this is a new one, which is C plus D. Now I know for sure that A does not make any difference at all to the covariance, right? A does not affect the covariance. Similarly, C, which is also a constant, it will not affect the covariance. So what is going to be affecting the B and the D? And that's what exactly we have over here. The B and D multiply whatever the B value, the D value, whatever that is, multiplied by the covariance of X1 and X2. That's it. That's it. So if you want to understand the covariance between two random variables, you look at B, which changes the variance. You look at D, which also changes the variance. And their overall effect is going to be B multiplied by D times the covariance. That's it. Okay. You might Not, you don't have to remember these things, this particular formulas and so on and so forth. But you know that, okay, what's the effect on that? That's what we need to understand. Finally, the fourth effect on the covariance between two random variables, it has to do something with the co-skewness and co-kurtosis. Remember, when we're talking about the first random variable, if we just move it to the right or left, the skewness was not affected, right? Kurtosis was also not affected. Here, when we talk about two random variables, just like we have random variable 1, random variable 2, we moved on from variance to covariance. Similarly, when we have two random variables, we'll move from skewness to co-skewness. Now, to be honest, it's really hard to actually make you understand this thing visually, but just understand, and the curriculum has also not gone into deep into it, is that yes, the fourth effect of a linear transformation on the covariance when we have two random variables is that it has to do something with the co-skewness and co-kurtosis. That's all that you need to know. Okay, so just remember that co-skewness and co-kurtosis. If you have two random variables, if one is moving, so the other one, does it become skewed, positive, negative, or there is no skewed at all, so on and so forth. That's hard to visualize, and that's something that we don't have to get deep into as well. All right, moving on to the variance of a weighted sum of two random variables, and this is a compute, that means we have to calculate it. So you should know the formula, and the formula is very simple. Okay, so if you want to compute the variance of two asset portfolio, okay, let's say we have two assets, okay, maybe TCS, one company, and IBM, another company. I've invested 50%, or let's say 60% in TCS and other 40% of my money in IBM. And if I want to compute the variance of the portfolio, the two asset portfolio, I can use this particular formula. Okay, what is it? The variance of TCS and IBM, that is going to be the weight in TCS, that was 60%, multiplied by the variance of TCS, plus the weight of IBM was 40% squared, multiplied by the variance of this IBM. Okay, and you have to square this thing as well, plus 2AB. What is AB? Is the weight of TCS, which was 60%. The weight of this is 40%. That's 2AB. Since we have two variables, so the covariance will also make a difference, multiplied by the covariance between x1 and x2. So covariance between TCS and IBM is something that I will have over here, TCS and IBM. You simplistically, you solve this thing, you get the answer. But as I said, it's not going to be that simplistic. Maybe they'll twist. They may not give you the covariance, they'll give you the correlation. Okay, so on the exam, you might be given not the covariance, but the correlation. You're given the correlation and the standard deviation. Correlation between TCS and IBM, you're given that, and standard deviation of TCS and standard deviation of IBM. You're given like this. Then no worries, just insert this thing, correlation, into standard deviation of 1, standard deviation of 2. Why? Because that's what the formula for covariance is equal to correlation multiplied by the standard deviation of this thing. So that is where these basics will help you. Okay, then after the variance, we need to understand what is IID, the independent, identically and independent distributed random variables. So random variables is independent. IID, it stands for independent and identically distributed random variables. So IID random variables are independent of all other components. They are independent as the name suggests. They are all from a single univariate distribution, from one distribution only. They all values, they come. If you're looking at a data of, let's say, ABC company, you're pulling out the samples X1, X2, X3. So they all come from the same distribution, right? And all have the same moments like mean, variance, all are the same. So all the data that the distributions that we have, they will all have the same mean, the same variance, the same moments. Okay, that's for the IID random variable. What about the features of IID random variable? The features, this is something that is important. The expected value, the average of the sum, when you add up all the random variables, okay, like X1, you have 4 random variables, X1, X2, X3, X4. The expected value of all the X1 plus X2 plus X3 plus X4, that is equal to the mu. The mu, what is the common n multiplied by the n. So if we have 4 random variables, 1, 2, 3, 4, that's 4 into mu, whatever the mu is. Okay, so that is the expected value of the sum of multiple or n random IID random variables. Okay, not just any IID random variables. So if I have 10 random variables and if I want to find the expected value of the sum, so that's expected value of X1 up until X10, that is going to be 10 multiplied by the mu. As I said, they all have the same moments, same mean and the variance. That's why we just take this n multiplied by this thing. What about the variance? The variance of the sum, the variance of the sum of X1, X2 up until X4, that is going to be 4 multiplied by the variance of each one, because they have the same moments. That's what we have in this same, the mean and the variance are same for all IID. Fair enough. That is something that we have for this thing. But pay attention, and this is very crucial. The variance of the sum of IID, it grows linearly. Fair enough. It's going to grow linearly. As this thing goes up, this thing will also go up. So there's going to be, it's going to go linearly. Fair enough. So if I have X4, maybe if I have X10, X20, so it's going to be 20 multiplied by the variance of that thing. But the important point, the variance of the average of multiple random variable, it decreases as n increases. Now here we are talking about the variance of the average. So when you take the average variance of multiple IID, when you take the average, that will actually decrease as your n increases. As your number goes up, we are saying that, okay, the sum will also go up, right? We have said that. But if you average it out, if you take your average, it's going to be lower. So let's say if I want to find the variance of, let's say, random variable, 1 to maybe X is equal to 15. If I want to find the sum of that, it's going to be 15 into variance, whatever the variance is. But if I take an average of all these things, of all these variables, the average variance, that is going to come down as n increases. Okay, so make sure that you remember these 2 points. Very, very crucial. All right, so with this, we end up with this particular chapter. All right, so let's start with another chapter, and that is reading number 16, which is sample moments. Okay, now it's really important that we understand the entire sample, the sampling, so on and so forth. Okay, so this chapter, it actually focuses on that and gives you a basics about the sampling and so on and so forth, which is actually used a lot. If I talk about hypothesis testing, you would see that there is no population data that you have. Okay, all you have is small samples that you take from the population, and then you make conclusions about the entire population. Okay, so it's important to know what is population, what is sample, the little bit of basics, and then we just go on. Okay, so this entire distribution that you see here, that is known as a sample, sorry, a population. This entire thing, this entire data that we have, that is known as population. Okay, for example, if you want to find anything, okay, maybe the returns on the index, let's say the Nifty index is this much, so all the stocks that is listed on the Nifty index, that becomes your population. If you want to measure the height of every male or female in the world, that becomes the entire population. Now it's very hard to reach out to the entire population, right? So what we do is we take out small portion of the population and we call them to be, let's say, samples. Okay, so the small things that you see here, the distributions, they are referred to as samples. Why? Because it consists of only a sample or small portion of the entire population. And in statistics, very often what we do is we work on these sample data and then we make conclusion about this population. Maybe I select only few people and I say that, okay, the entire population looks like this. The entire people in the world, they have a height, weight, anything that I'm interested in, I can make conclusions about that. So that is the reason why it's really not possible to reach out to everyone or select or do research on every company. And that's the reason why we study the samples. Now, moving on to important things first. The very first thing is that you should know what these things are called. Okay, otherwise you'll get confused later. First thing, what is a population parameter? For example, the mu, this thing that you see here, okay, and the other thing is the variance, right? So the mu variance of this distribution of the population is known as the population parameters. Okay, they're named as parameters. So you have to remember, okay, if I tell you that what is a parameter, I'm talking about the population data, specifically the mean and the variance. Now, if I talk about sample, whatever mean and variance I get for the sample, I call them in statistical language, I call them a sample statistics. Okay, so often you will, when we talk about confidence intervals, so on and so forth, often you'll hear that, okay, what is statistic, sample statistic? So exactly what we are meaning is that we are trying to say that, okay, sample statistic is mu hat, this hat symbol that you see, that refers to sample data. Okay, so sample statistic, it consists of mu hat. Then the mu hat is also referred to as sigma, sorry, X bar. This line that you see here, that's X bar. Also for variance, we say that, okay, it's S. This stands for sample variance, or maybe we can say sigma square hat. Okay, so make sure that you know these things. What do we mean by, if I say that, okay, what is mu hat, I'm essentially referring to the sample statistic. If I'm saying the X bar, that's the sample mean, sample statistic. The variance, the variance. Okay, that's something, just a differentiating point that you should know. Otherwise, you'll be confused. Okay, fair enough. Now, these things, let's say I've taken a sample, a small sample of, from this entire population. I've taken one sample and I found the mean of that particular sample, and the mean, the answer is 10. Okay, now what does this 10 actually means? It's referred to as a point estimate. See, we are estimating, we are finding something, right? So this answer is referred to as a point estimate. Why point? Because it's only a single value that I have. And that's why I say that it's a point estimate. Now, how do I come up with this mean is equal to 10, this sample mean mu hat is equal to 15, this mu hat is equal to 18, the mu hat is equal to 45. How do I come up with this number? So, well, there is a formula for that, and it's very simple. Okay, so it's known as, to calculate this sample mean, I can refer it to as two ways, which is mu hat or x bar. And what are these called? These are called sample statistics. Okay, so if I want to find the sample mean, all I have to do is take all the observations in my data. Let's say from this entire population, I've picked up here maybe just 10 people. I went to 10 people, I measured their height or weight or whatever that is that I want to find, and each of those individual, I'll note down their height, their respective height. Okay, so let's say these are the weight, the returns, whatever data that you have collected. I went to only 4 people. Okay, in this particular sample, I went to 4 people. I did a research. I measured their height, whatever the interest is, and then I'll just take a sample mean. Okay, so I'll just add up all these things divided by 4 people in the data, just a pure arithmetic mean formula, and I get the answer as 18, which is what I have over here. The mu hat is 18. Similarly, I found for all the other data points. And what are these called? They are called as point estimate. So this formula is known as estimator. It is known as estimator because it helps you to estimate your sample statistics. Okay, so this formula, we say that, okay, it's an arithmetic mean formula, but in statistical term, it's known as estimator. That's it. All right, so moving on to the sample variance. Can I find the variance of these samples as well? Yes, I can do that. The formula is very simple. It's x, this whatever the x value is, x1 is 15, x2 is 19, x3 is 22, x4 is 16. I take each of the data. For example, first one, I take 15 minus the mu. Mu is what? The sample mean, which is 18. I take this, I square it, and then n. Okay, I'll just first add all these things. Okay, then plus the second data is 19 minus the mu. Mu is what? Again, it's the mean is constant. I square it. I square all these data. Okay, and then I add up all these things. They are all plus, so I'll add up all these things, and then I'll divide by n minus 1. What is n? N is a number of people that I went to, the observations. Okay, over here I went to 4 people, so n minus 1, it has to be in the denominator 3 people. Okay, and then if I go ahead and if I calculate all these things, I will go ahead and I will get my answer, the sample variance. Okay, and the answer that I'll get, it would be referred to as an unbiased variance. It's important that, okay, we are estimating this, sample means, and what we do is, once we estimate that, we say that, okay, yes, the height should be 18, the weight should be 18, the return should be 18, so on and so forth. So we are concluding the entire thing is 18, right? We are concluding that. Now, just with 4 people, I cannot do it actually, but still we are doing it. That's what statistic is all about. Okay, so this calculation that I got here, this is known as unbiased, okay, which is a better. So on the exam, if they ask you to calculate the sample variance, n minus 1, take n minus 1, you will get a wider variance, which is more reflective of your population. Is there any other version? Yes, that is known as a biased version, wherein you just have n in the denominator. Okay, this is known as a biased, but on the exam, our preference is to calculate unbiased. Always and always use this. If they specifically ask you that, okay, calculate the biased, then you do that. Okay, what about the standard deviation? Standard deviation is the square root of this variance. Simple. Okay, moving on to the next learning objective. Explain the difference between a population moment and a sample moment. What are moments? Moments, it helps you to describe your data. So here, two moments that we are looking at is the mean and the variance. Fair enough, no problem. Sample mean and variance is called sample moments, while population mean and variance is called population moments. So in order to find the population mean, all you have to do is a simple average. If this is my entire population, if I want to find the sample mean, all I'll take is sum of all the observations x1, x2, x3, so on and so forth, and divided by the number of observations that I have. Simple arithmetic, pure mean. What about sample mean? Can I calculate it? Yes, the same formula, no change at all. Okay. What about variance? Variance is the same, x minus mu squared divided by n for the population variance. For sample variance, what do? We take x minus mu, we square all the data points, and then we have n minus 1. That's the only difference that we have. Okay. Then moving on to the estimator and an estimate. Okay. So what is a point estimate? Point estimates are single sample values used to estimate the population parameter. Something that we have already, I told you about. What is an estimator? Estimator is a formula that is helping us to calculate the mean or the sample variance and so on and so forth. So that is known as the estimators. Fair enough. Then we have something known as the bias of an estimator, and explain what the bias measures. Now, the bias is something that is a difference between the expected value of the estimator and the true population value. Understand what we are doing at a very high level. What we are saying is we are using these sample data or the sample statistics that we get. We are actually predicting a lot about the population. Okay. So if I select only maybe 10 companies in the stock market, and then I'm making a prediction about the entire stock market just by selecting 10 companies. If you just think about it, 10 companies, very small sample, they're not reflective. They cannot say much about the entire population, right? There's going to be a bias. Okay. There's going to be a bias that this answer that you got, okay, maybe this answer, this mean or this sample variance that you got, there's going to be a little bit of bias in there. So when I talk about this bias, yes, there's going to be there of an estimator, the sample mean or sample variance. So the bias, it measures the difference between the average of the estimator and the true population value. The mean of 60 was a true population value. Now, all you have to do is to remember at this point in time these things. Very important for the exam. Okay. So remember, sample mean is unbiased. Why? Now remember, I'm going to share two things. The first thing is the unbiasedness. I'll just take 2 minutes time. Unbiased. And the second thing is consistency. Whenever we are working with sample data, okay, very two desirable properties that I want in my sample statistics is unbiasedness and consistency. Unbiased means there is no bias, zero bias, right? There is no biasness at all. And the second thing is consistency. Consistency means whatever I find in my sample data, the same thing will exist in my population data. Okay, whatever I conclude, that's going to happen in the population. Fair enough. So when I talk about this bias of an estimator, the sample mean is unbiased. So it's fantastic that the sample mean that we will calculate, that is going to be unbiased. Why? Because if you look at this thing, what is the bias formula? The bias is the expected value of the mu hat, the sample, minus the original population, which is mu, the population sample, that is equal to be 0. that is going to be 0. So if it is 0, bias is 0, that means it's a perfect thing. That's what we want. It's unbiased, right? So that's what happens with the mean, because what we are saying is, if remember in the last chapter when we were talking about the IID, we said that, okay, if the data is IID, all the samples, all the data will have the same mean, which is mu. Okay, just for your reference, if we go here, you see this thing. Okay, if the data are IID, okay, they all have the same moments, like the mean and the variance. The mean is going to be the same, which is 4. Even if I have 1, 2, 3, 4, how many data points I have, the mean is going to be the same. So if the mean is going to be the same of the samples, if the data is considered to be IID, and if the mean is the same, then I can say that, okay, this will also have a mean of mu, and this is already minus mu. So mu minus mu, that is going to be 0. So the bias is 0. Right? And that's why we always say that, okay, sample mean is unbiased. What about the variance now? The sample variance. That has a problem. Okay, and that is known as a biased estimator. So when you estimate the variance, the dispersion, that is going to be biased. Okay, now there is a reason for that. If you take the expected value of the sample variance minus this thing, okay, something that is going to be left out. If you establish or if you expand this thing, there's going to be a different formula. There's going to be a derivation and so on and so forth, which I really don't want to go at this point in time. But as I said, remember this thing. Sample variance is a biased estimator, because eventually this answer, it doesn't turn out to be 0. It doesn't cancel each other out. Okay. And you have n at the denominator. So the sample, if I talk about the biasness of the sample variance, it has this. And that is the reason we say that, okay, when the sample size is large, the bias is small. If you pick up large samples, the biasness will be small. As in this example, if you see here, it's 45, the mean, and this is 60, so very close to it. Okay, so mean any which ways is a unbiased, and the variance will also be very much similar if you pick up a large sample. Okay, that's something that we need to understand. Now, moving on to the next learning objective, what is meant by this term, which is blue? All you have to do is you have to remember this particular thing. What is blue? The best linear unbiased estimator. We have just seen what is unbiased. The mean is unbiased. Is the variance unbiased? No, that's not unbiased. There is a problem with it. Okay. And that's the reason the mean, the variance is unbiased. So can the variance become the best linear unbiased? No, it cannot. So which parameter or which statistic can become? It's the mean. So the mean estimator is blue. Why? Because it has got the smallest variance of all the other linear unbiased estimators. Remember this thing, blue is a property which says that, okay, best linear. When we take, there are many methods to actually find the data, right? So mean is one, sample mean is one way that you can find the data. There's some other method exists also. Okay, so out of all these methods, the mean estimator that we are studying in this particular chapter, that is considered to be blue, the best linear unbiased estimator. Why? Because it has got the smallest variance. Then we have the consistency of an estimator, and explain the usefulness of this concept. As I said, two properties, very, very crucial, and that is the consistency. Consistency, it's a desirable property of an estimator. The estimators are the mu hat, the sample mean, and the sample variance, or I can say variance sigma squared hat. So consistency is something that as a statistician, okay, as an analyst, I want two things. My estimator should be unbiased and my estimator should be consistent. Now, property of consistent estimator. If the sample size increases, the bias will be 0 and the variance will also be 0. Same thing it talks about, just in another terms, nothing like that. So that is the property of a consistent estimator. What about law of large numbers? It says that as the sample size increases, the estimators, they become consistent. Let me show you this thing. Now, this is this thing over here. It's a huge sample. I mean, I cannot extend this, but this entire thing is the population, and we have this thing mu here. And then this blue one, this thing, as you can see, it has a X bar, or maybe I can say this orange one is something that you see here. This is another sample. This blue one is another sample. And this entire thing is the population. Now just notice one thing. If I pick up a small sample like here, and if I get the mean here, and the original mean is here, see the distance, the variance. It's very much, right? The dispersion is very much. I'm saying this, but the answer is this, right? On the other hand, if I pick up this blue one, if I take a large sample, now if I draw their mean, so this is mu, and this is my sample mean. See the variance, it has gone down significantly. That is a law of large numbers. It says that if you pick up large samples, the mean is going to be very close to your original population. That's what it says. And that's what consistency tells you, that if you increase the sample size like this, then the biasness will be 0 and the variance will also be 0. That's what the thing tell you. Okay, so if sample size increases, bias will be 0, variance will be 0. Law of large number, sample size increases, the estimators, they become consistent. They become consistent means 0, 0. And one assumption that you need to remember is that the law of large number, this thing, it assumes the mean is finite. Okay, they assume that the mean is the mean that you get the X bar or this mu, they are finite. Okay, remember that at this point in time. What about the central limit theorem? Well, the central limit theorem, it says that as you pick samples, the overall sampling distribution will become approximately normal. Okay, let me just show you. So let's say that if I have picked up these 4 samples and their sample statistic, the mean is, sample means are these. Now, if I draw a distribution of these sample means, if I draw a distribution, okay, let's say the 10 is here, 15 is it's here, then 18 is here, and then 45 is, let's say, on this scale. And if I draw a distribution, okay, it's gonna form a pretty much, it's gonna look like a normal distribution. It's gonna look to be a normal distribution. That is what central limit theorem tells us. So it tells us that, okay, as you pick more and more samples, and if you plot the sample means, the X bar, if you plot them, okay, even if the original distribution is not normal, but then the central limit theorem says that as you pick up more samples, their sample means, okay, when you create a distribution of all the sample means, when you create a distribution, which is known as sampling distribution, the final distribution will look like a normal one. And then you can use this normal distribution. You can use this normal distribution in your hypothesis testing. Okay. But this one, I cannot use that because it's not normal. And hypothesis testing, it says one thing. If the distribution is normal, use it. Otherwise, not possible, which we will see next. Okay. But I hope you get the idea of the sample central limit theorem. Fair enough. That's what it says. One thing that you need to understand is it assumes that both mean and variance is finite. Law of large number, it says mean is finite, but it assumes that mean and variance, they both are finite. Okay. It doesn't go to any number it picks up. Okay. What are the properties of central limit theorem? Property is that the mean of the population mu and the mean of the distribution of all possible sample means are equal. So the mean of this distribution, the sample, the sample distribution that we just created out of all the sample means, that mean and the population mean will be equal. That's the first property. The second thing, the variance of the distribution of sample mean is this. The sample means, the variance is going to be sigma squared over n, which we saw unbiased. The population variance divided by the sample size, thus it approaches 0 as the sample size increases. So ideally, the variance is going to look like this, sigma square over n. Okay, the same thing with which we saw in unbiasedness. But as the sample size increases, as the n goes up, the denominator goes up, the overall equation comes down. So it becomes close to 0. Okay, so these are the two properties that you should know about this, the central limit theorem. Then we move on to something that we have already seen, and that is the skewness and the kurtosis. So skewness is the third moment. Okay, it refers to the extent to which the distribution of data is asymmetric around its mean. Okay, so this is the formula. If you want to calculate that, all you need is the x, whatever your data point is, minus the mu, which is the average, divided by, to the power 3, because it's the third moment, divided by standard deviation cube. Okay, I've cubed because it's a power 3. You calculate this, you get your skewness. And skewness will tell you how your data looks like. Is it negatively skewed? That means a lot of data points are here. If a lot of data points are here, then that means it's a negative skewed. And if it is negatively skewed, then that's a bad situation. All the negative values are coming. These are all positive values. These are all negative values. But if all negative values come, is it good? No, it's not good. Negative is always considered to be bad, right? So the overall thing is that if you have a negatively skewed, that's a bad situation. On the other hand, you can also have a positive skewed data. When you calculate all this with this formula, and if you get your data points like here on the positive side of the distribution, congratulations, that's a very best thing. Okay, so that is something that you should know about the skewness. What about the kurtosis? Kurtosis is, it tells you about the peakedness of your data. It actually, if this is normal distribution, it pulls up, the kurtosis, it will pull up your normal distribution. And as you can see, this is blue one is a normal distribution. It's got pulled up by this another distribution, which is known as the leptokurtic. This is a bad thing. Leptokurtic is a bad kurtosis behavior. So it refers to how, what do you mean by kurtosis? It's the fourth moment, and that's the reason you have, over here to the power 4, and in the denominator we have standard deviation to the power 4. Okay, it refers to how fat or thin the tails are as compared to the normal distribution, and ideally it tells you about the peakedness. If you pull up, okay, the tails is going to be stretched out, as you can see here. The tails are being stretched out, and that's the reason the leptokurtic is bad. On the other hand, we also have another, name, which is known as platykurtic. As you can see, this particular distribution that you see here, this one that you see, the red one, okay, that's known as platykurtic. Platykurtic means it actually pushes the distribution, normal distribution down. So it's like a plateau kind of a thing. It's a flat thing. That's what it does. Okay, platykurtic. Not a very bad situation. Okay, as compared to normal distribution, not a bad situation. But leptokurtic is bad. Positive kurtosis or leptokurtic is bad. High kurtosis is bad. Negative skewness, it's risky. Okay, moving on to the next learning objective. What is quantiles? I've already told you about the quantiles, but just to let you know, the two quantiles that we are studying is the mean and the interquartile range. So what does the job of a median? As I said, it picks up the entire data, divides into two, the center, the center point, it picks up that. Okay, what about the interquartile range? So as you can see, this is the median. It divides the entire distribution into two parts, 50% here, 50% here. That's what it does. Its job is to divide 50% data here, 50% data here. That's it. And the center point is a median. What about the interquartile range? As it says, it look here at the interquartile diagram. It divides the entire distribution. Okay, so this is median or mean. Okay, let's call it median actually. So if this is my median, just a minute. Okay, this is my median. So what it does is within this median, this interquartile will divide it here and will divide it here. Okay, so I can say that this is 25% of the data, and then this is this 75th percent of the data. So the interquartile range, it divides the distribution into two parts. Okay, the first is 25th. Okay, 25th of quarter 1 and quarter 3, and then it tells you that okay, how much data is clustered around the mean. So it gives you a visual look. It tells you a lot that okay, whether your data is clustered around the mean or whether it's too far away from the mean. So if the data is clustered around the mean, you know that okay, it's gonna be, if you invest your money maybe next day or something like that, it's gonna be near about the mean. Okay, so that's what interquartile range it tells you. It studies the middle 50% of the data. Note, median and IQR, they are not affected by outliers, which is why they are better than the mean, which is easily affected by the outliers. Okay, so that's the reason we prefer to use the median. What about the mean of two variables and apply the CLT? Now, here we just need to understand that, okay, we can find the mean of two variables, same sample mean formula that we have studied. So if I want to find the mean of X variable, and if I want to find the mean of Y variable, I'll find this individually and I'll find this individually. Same thing, no difference at all. For the IID data, we can apply the CLT and examine the joint behavior. That means you can find their, in a vector shape, you can go ahead and you can find their overall understanding as a joint behavior, as how do they behave both in, when they are joined together. We don't have to get into this overall vector, but understand that yes, these two lines is something that you need to know. Sample means is something you calculate for X. For TCS, you calculate the sample mean. For Reliance, you calculate the sample mean. That's it. Individually that you do. That's it. What about the covariance and correlation between two random variables? Covariance means that we are talking about two variables. How do they move together? One goes up, other goes down, so on and so forth. So it tells you about the degree to which two variables they move together. If you want to find the covariance, you take the observed value minus the expected, the average, X minus mu, and over here Y minus mu. That's it. You take finally the expectations, the average. That's it. You get your covariance. Okay. What about correlation? The problem with covariance is that it can range from negative infinity to positive infinity. You can have any value, which is incomparable. So correlation is a standardized measure, a better measure than covariance, and its range is between -1 and +1. So no matter however that you calculate your correlation, the answer is always going to be within this boundary, within this range. So to calculate the formula of correlation, the covariance between X and Y divided by the standard deviation of X, standard deviation of Y. Make sure that you remember these formulas. I really feel that, okay, not exactly they're going to be tested, but it's important. Okay, what about the next learning objective? Co-skewness and co-kurtosis. Now, this is I would say it's a very complex concept to be learned at this point, but let's just go through it. Co-skewness, it measures the likelihood of large directional movements occurring for one variable when the other variable is large. Essentially, what we are doing is, when we talk about the co-skewness, is that we had this variance, right? We had this variance and we said that, okay, if I have one variable X and if I have one variable Y, if this thing is moved, what happens to this? That's what the covariance tells you, right? The correlation tells you that, okay, if you have if this goes up, what happens to this one? But now similarly, if this X, okay, if this data is skewed, then what happens to the Y? What happens to the Y? Does it also become skewed, or is it normally distributed, or is it a positive skewed? What's the response? That's what the co-skewness tells you about. It measures the likelihood of a large directional movements. Remember, large, because outliers are extreme, it's large. Okay, they're going to come here. So if one is skewed, what happens to the other? Okay, so large directional movements for one variable when the other variable is large. So we are trying to find, it measures the directional movement for one, which is Y, when the X is skewed. That's what it does. Co-skewness is 0 if there is no change in value Y due to a large change in X. So if this thing X is skewed and Y is not skewed at all, we say the co-skewness between these two is 0. Okay, remember these 3 points. That's all that you need to know. Co-skewness is always 0. Okay, can you explain again, sir? I didn't get it. Okay, no problem. So basically what we are saying is, in co-skewness, we are saying is that, okay, we observe one variable, which is, let's say, X. What do you mean by co? Co means two things, right? Two variables. And we have another variable Y. Fair enough. And we pull up this data and we see that, okay, our original distribution is skewed. The X variable is skewed. Now, let's see the effect on Y. Is this also skewed, or it's not skewed? If there is no change in Y, no change over here, then we say that the co-skewness is 0. But if the data for X, let's say TCS, the data is skewed, and for IBM is also skewed, then we say that yes, the co-skewness is that is there. If this is skewed, then this is also skewed. We can say that yes, there is a co-skewness. Fair enough. But if there is no change to IBM because of TCS, we say that, okay, there is no change in, yeah. So that's the overall thought process that you need to have for co-skewness. Remember, skewness, it measures the large movements, the outliers, right? Now, here is a point that I need you to understand. Co-skewness is always 0 in a bivariate normal sample because the data is symmetrical and normally distributed. Okay. Now, what do I mean by that? If you pull up a bivariate normal sample, what is a bivariate? Bivariate means 2. Okay. If you pull up, let's say this is one sample, this is already a normal distribution. Okay. If you pull up 2 samples, let's say this one, X, and let's say this one, which is Y. So if this original distribution is normally distributed, then any data that you pick up, this one and this one, they will also be normal. So if they are normal, as I told you, in a normal distribution, the skewness is 0. That's the standard property of a normal distribution. The skewness is 0. So if you pick up any data from the normal distribution, like over here and this